To kind of start with, there's a project that I talked about yesterday, and the notebooks that we shared are kind of like a souped up kind of tutorialized version of the analyses in that paper. So there's kind of like three components. There's like our NLP analyses, our dream coder, like this library learning neurosymbolic thing that has a notebook, and then our kind of probabilistic convention formation model has like I tried to port it to Python, and it probably has some bugs in it, but it runs at least. So I'll keep working on that. But it is like, conceptually it's there, but there may be like, the math might be a little off or something. So that's the notebooks I shared. I wanted to give kind of a little bit of an overview first, though, about kind of how I think about these kinds of models. So this is like, I guess I was talking at lunch about like, I feel like I was trained in kind of multiple modeling traditions. So I think of it just as a big toolbox of different tools for thought, right? So each model kind of instantiates at some level of abstraction, some kinds of hypotheses or theories. And like, often there are deep commonalities underneath the modeling frameworks. So like, for a long time, there's this like big fight between, like Bayesian modelers and like connectionist modelers, right? And they seem really at odds on the surface, but you can actually show that like there's a one-to-one correspondence where you can like set up the objective function of a neural net to do basically what the Bayesian model is doing, and vice versa. You can like set up some kind of graphical model on the Bayesian side to kind of do what the neural net's doing. Algorithmically, of course, they're doing very different things, although like you can use neural nets to do inference in Bayesian models, and you can use Bayesian neural nets, and they're kind of like not actually as at odds as you might think. So in order to see those commonalities, though, you kind of have to like keep an open mind and be comfortable like looking at things from like different lenses. So I wanted to start out with the kind of more probabilistic side, since I think it's been pretty influential in social cognition recently. And then at the end, I'm gonna get into like how we might bridge that with like this new generation of neural nets. So I'm interested in this question, like many of you. And I think that like this idea that we heard about this morning from Jonathan is that there might be some stuff going on inside other people's minds, and we want to maybe represent that in some way in our own mind. So this is kind of, I feel a little bit like I have to, like, I could spend this entire time probably being like, okay, like, here's how you would do what Jonathan was talking about, like in this framework, but I'm going to try not to get into that. I think of this as like a framework, not like a specific model. So it's like a way of writing down theories, and you could like write down the kind of factive theory of mind that Jonathan was talking about inside a model like this. And it would like reduce to the kind of propositional set-based things that he was kind of putting on his slides. But like, this is maybe like the bigger, I think that there's this notion of like expressiveness in model classes, which is basically like, as like a language for writing down theories, like how much of theory space can you cover, right? So ideally you would like something that's like capable of expressing the like maybe more recursive things that Jonathan was talking about, even if you think that like that's not a good model of cognition, right? Because then if you can write down both theories in the framework, now you can test them and stuff. So that's good. So in this idea, in a kind of probabilistic framework, it all starts with a forward model. So the idea is that I can imagine, like, if I were this person in this context, seeing these things, I might have these beliefs and I might have these desires. And if that's true, what would I do? Right? So it's basically like, given all of these things, I can make some predictions about what the actions that other person might take are. And actions here can be basically anything that is observable. So it's like anything I look at you, I see you like move your face, that's an action. I see you say something out loud, that's an action. I see you like walk over and fill up your water bottle, that's an action. These all can be kind of expressed in this way. And the problem of Bayesian inference is like, given that only the actions are the things that I can see, I want to like make guesses about what I can't see. Okay. So I might want to know like, okay, I see them like, filling up their water bottle. And I have a kind of forward model that's like, well, if their water bottle was already full, they wouldn't have done that, because that would have been a weird thing for a rational agent to do, is to fill an already full water bottle. So that would assign like low probability to the action of filling up your water bottle. Whereas like another set of these things, like, oh, empty water bottle, or like you saw some dirt in your water bottle or something else, makes those actions more likely. So the basic idea of Bayesian modeling is that it just gives you a way to like flip this and like say, conditioned on observing some things, what do I think is the generative process that led to that? Okay, so how does this work in social cognition? And like, I think about communication a lot. So this is kind of a traditional model of communication that you can kind of write down in a Bayesian way. So I was originally going to put some of this in the talk yesterday, but I was like, okay, there's like a little bit of math and stuff, so maybe this is a good thing to put in the tutorial. So you can have a little like model of transmission where I'm trying to convey some thought in my head to another person, but unfortunately we can't read each other's minds, which would make that easier. And it has to pass through like something observable first, right? So we have to make some signal. And this is like often vocalizations or text, but it could also be like a drawing or some gesture, or basically anything like a thing that you draw, like make a line on in the sand or something, right? Anything that's kind of observable by another person. And then I have some idea of like a forward model of like, how does a person observe some signal, which I'm calling U as like an utterance, and make a guess about what the kind of like object about that that was intended to be conveyed. So this is kind of reducing to an example of like referring to things. So we use language for lots of stuff, but like a lot of it is complicated, and these models have kind of been extended to that. But the kind of like fruit fly of this is often like, if I want you to have the idea of like this thing in your head, what do I say? So I might say like the yellow thing. And like in some contexts that might make you think of the thing that I want you to think of. But if there's like a bunch of yellow things around, that may not be so good. Okay, so this is kind of the thing we're trying to set up a mathematical description of. So a very simple thing that an agent could do is kind of rank the possibilities of what it might refer to by some little function that says, like, based on my knowledge of language, does that utterance, like, is that true of this object? Okay, so like, this is just a binary thing that says, if it's like yellow thing is true of that, but it's like not true of this, right? So 1, 0. And now I just renormalize. So this basically would assign high probability for yellow thing to that and low probability to this. So now that's the listener side. Say I'm a speaker and I want to say something that will successfully get you to think of the thing that I'm trying to get you to think of. We write this as a little kind of softmax decision rule. So this basically says like, sometimes these things can be negative. So you put them in exponential so that they're not negative. It's the main reason you do that. And then there's some utility of like saying different things given that you want to refer to some objects. And then this is kind of like, it's called a temperature parameter. So it kind of like controls, if it's really big, you just always say the one utterance that's best, it's maximizing. And if it's 0, you're uniform. So basically you like are equally likely to say everything. And then the question is like, what is the utility, right? How do you say whether a particular utterance is good or bad? And this is where a lot of the kind of research happens, is kind of like playing with different utility functions. But a very simple one you can write down is, I want to be informative to the listener. So this is recursion, right? So I form, like I, the speaker, run this little function and come up with like the probability that they'll think it's, oh, if I say this, and then I kind of loop over all the different things I could say. And some of them will make the listener more likely to think the thing I want, and some will be less. And this log is kind of an information theoretic thing that's like surprisal. So it's like, the more information I'm able to give, the more I'm able to like reduce their uncertainty, the better about the correct thing. And then we also can add other stuff like a cost term. Okay, so this is kind of like a first glimpse at a probabilistic model of communication. So this is kind of like the most traditional way that you might specify, like I'm communicating through a noisy channel. And I'm trying to say something that like when my partner tries to invert it, they're gonna get what I intended. And obviously there's lots of ways of elaborating this, but so I kind of, when we were getting into this project, was thinking about like, you know, this model isn't gonna work anymore. So I'm thinking about like this block building task because like, because of some things. Okay, so here's 2 things that I think make it not work anymore. One of them is, okay, suggested by this example, which I really like. So this is an article from Grantland, rest in peace. It was a kind of site where people wrote very like niche things for sports fans, which I am not one of. So I loved just logging on here and just getting my head blasted because I never knew what the heck they were talking about, ever. So will Mets make Kansas City expand? What the heck does that mean, right? So are we talking about the city expanding? Like, are we talking about like suburbs or, okay, so then I didn't know you could groove first inning pitches. I don't know like what that means. I don't know what it means to pitch around Royals, right? So I don't know what that would look like. And then, you know, you keep reading and it's like, you just start seeing these numbers and four-seamers and stuff. So this is like written for experts in the domain of sports. And I think that like the clue that I take away from this is 2 things. One is something that I think we've gotten a lot of this week, which is, you know, there's real individual differences in the people you're talking to. So you can't just use a monolithic model for everybody. And if you're kind of thinking about this in terms of like what Jonathan was talking about this morning, like the cookie monster, it's like, well, some people like cookies a lot, and some people, you know, that they don't want that kind of cookie. They just maybe you've experienced they can't eat chocolate because they're allergic to it or something. So you're like, okay, they probably don't want that. And now you need a way of saying, okay, I have a map for this person and I have a map for that person. So this is already introducing some kind of like partner specificity or like individual specificity in the kind of models you're holding for how to communicate with different people. So if I'm talking to like a sports fan and I'm a Grantland writer, I can use all this lingo, right? But if I were like on, I don't know, NBC or something, maybe I would get kind of like my knuckles wrapped and be like, you can't use that stuff here. That's like, our viewership is like not that kind of, expert. Okay, and then the other problem is this like non-stationarity problem. So that's like a fancy term for things changing. So if you tried to write down that listener model and that like L function, I'm calling it the lexicon, right? So the lexicon is the thing that allows you to know whether a particular word means a particular thing. Vast oversimplification, but that's like a thing that you could say about the lexicon. You wouldn't have baseball stuff at all in the 1800s because it hadn't been invented yet, right? So like four-seamers, bases, like, I don't know, shortstop, that's a baseball word. All of these things would kind of not be in your like mind at all. So like when baseball was invented, you clearly like under a kind of static dictionary, you wouldn't be able to like talk about it, which would be a problem because, if you like something, you want to talk about it. So there's kind of this idea that we need to enrich this model because the problem is that this is assuming that there's kind of fixed things in each person's head that you can always just encode and then assume that the other person has the exact same stuff in your head to undecode. So inverts back to your thoughts. And this assumption, I think, as many things have revealed this week, is kind of not always reliable. So you have to be able to like update them. So that's what a lot of my kind of modeling work is focused on, is like, how do we come up with a model where you can allow these things to change as a function of who you're talking to and what you're needing to talk about. So this is kind of a adaptive model of meaning in social interaction. So I wanted to like give you a little view into like how we might think about that as like a computational account. So there are kind of 3 steps to writing that idea down. The first one is that like we previously just had this fixed function, but there's this kind of move you can make, which is like take a fixed thing and allow it to change. So you can parameterize it. You can say, now I don't just have a single L function. I actually have a big family of L functions controlled by this parameter phi. And you can kind of thread that through the whole thing. So you can say, now I have a speaker that, and I can say, here's what they would say if they were assuming this was the lexicon. And now this is a very, very common move in probabilistic models. Is my advisor always called it lifting a variable. So it took me like 3 years in the lab to figure out what that meant. So that's actually an example of this kind of when you join a lab, it feels like they're talking about baseball. But you can basically say like, if I don't want to fix something and I want to write it like this, where I take out the variable that I care about, I can basically put a distribution on that variable and then marginalize over it. So this operation is called marginalization, where you're basically a fancy way of saying like taking an average over stuff with respect to a particular variable. So you can write a listener that is reasoning about the speaker, you can write the speaker that's using their utility. And in both cases, they're kind of weighting different utilities by how likely it is that their partner is using that particular lexicon. So once you've had this pair of steps, you've allowed something to change, and then you've put a distribution over it. And this is called a prior. And then the kind of cooler thing then is that you can update your beliefs about that thing based on observations, okay? So this is like, I think, very characteristic of probabilistic modeling, where you're like, there's some assumption here that I kind of don't like. I'm going to relax that assumption. I'm going to introduce it as kind of a probabilistic thing instead of a fixed thing. And then I'm going to learn about it. Yeah.
So as we're learning, so BI is basically like an entire dictionary of all signal meaning mapping. So
Yes.
You're not learning about signals in isolation, but it's more like about a different
holistic thing. Okay. Yeah. And like, if you're kind of smart about this, so I think a lot of kind of arguments about Bayesian things come down to, people arguing about like a common criticism is like, well, how'd you pick the prior, right? And this is especially true in like Bayesian data analysis, where you're like doing statistics and you're like, hey, like my model is better. And they're like, well, you used a prior that said your model was better. That's not a good model comparison, right? So we're doing something a little bit different here because we're using this as a cognitive model. So this is basically like trying to say something about what's in people's heads. And this idea is that sometimes you don't know ahead of time what like dictionary your partner is going to be using, right? So I don't know ahead of time whether I'm talking to like a big baseball nerd or somebody like me that's not a big baseball nerd. So a lot of like social expectations can be kind of encoded in a prior like this. And when we're like doing research, there's kind of two moves. One is to elicit this independently. So you just get a totally separate group of participants to like score. You just can ask them questions like, you meet a new person, how likely it is that they would use this word in this way, right? And do that and build up a distribution. Or you can try to like be fancier and be like, I'm going to try to learn what participants' priors are from the data. But this is kind of like background for the notebook. But I think we're kind of out of time or running out of time. So maybe I just want to give you like a brief tour so that you can look at it on your own if you're curious. So there are 3 notebooks I prepared. The first one is a bunch of natural language processing analyses. So this is basically pulling in this notebook of the block construction task. And you can do things like, count how many words people used as the task went on. You can look at particular referring expressions. So this is like looking at the distribution of words. And then you can do fancier things that may not have rendered, but you can like make plots like the one that I showed where the arrows go to different places as kind of like in an embedding space where do these trajectories of referring expressions move around. So that I thought would probably be the most boring for you because you've already heard a lot about how to do that. So this one is, Dream Coder. This was like a nice little, nice big paper where the argument is that you can take various domains. So here's some towers, right? but here's some like graphics, here's some plots, other types of things. And you can basically try to look at a bunch of those things and pull out little functions that help you express them in a more efficient way. So it's basically like, in the case of graphics, this is the problem of configural learning. So you see a bunch of stimuli and you want to know like, okay, there's a little fragment that like is in common across all of these different things. And I want to pull that out so I can use it as kind of like a chunk, like a visual chunk. So we wanted to run that for our towers. So you can write like a little, it's called a domain specific language, a DSL. So this uses a particular library. So you have things like H places a horizontal block, V places a vertical block. This moves your hand like around. And basically any tower can be written like this. And actually, like if I'm just loading this in GitHub, but if you ran these, you would like visualize towers. And then you can run this like library learning. So you basically give it all these little programs and are like, hey, come up with a new Python package for me, right? And I want that Python package to like make my code better. And by making my code better, I mean, I can, instead of having to like, every time I, want to run a regression, I don't have to like re-implement the entire regression thing. I can just call the like regression model function, right? So this is basically saying like, give me functions that allow me to code more efficiently in this like dumb little tower language. And what you get is these chunks that have, again, if you ran it, you would see these little chunks that are like lambda something, 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 and maybe have arguments and are like, you can kind of like rewrite that original program as like, instead of having to like place a bunch of blocks and then go over and place a bunch of blocks, you can just be like, place the L, go over, place the C. So that kind of like multi-step process got kind of like grouped up into like a little like API, and you can just be like, do that thing, and it can like hit it. So this is kind of, we've been working with these for a while, and this kind of like library learning thing, and I found it really hard to get into because this is like a joke about Armando, who is like the lead author of this. It is kind of like his lab that did a lot of this, and he's like one of these just astoundingly good engineers that is like completely inscrutable. It's like everything just works so well, but if you try to look at it, it just like blinds you like the sun. So that's like, we were hopefully trying to like write this in a more like hide some of the hard stuff that I still can't understand. So then the last thing I wanted to show you was a implementation of this little communication model. So you have these little lexicons that give you whether a particular utterance applies to a particular set of actions in this like block world. And then you can write down these like these agents that have a role. They're either a speaker or a builder or architect. They have a set of affordances, like actions they can take. They have beliefs about what the language means, and they can act. So if you're the architect, acting is picking an utterance, and you can act as a builder by picking an action, like a block placement. And then you can simulate them. And then this is kind of like the Bayesian stuff. So you can write down like this recursion where I write a builder function that just takes in an utterance, loops over all the possible actions, kind of scores them relative to like whether their language means that thing, and returns the distribution. And then the kind of recursive part is that the architect like calls the builder function and the builder calls the architect function. So this is kind of like very, very, very rudimentary like theory of mind. So it's basically like, I'm simulating what a person with these beliefs would do, right? And as you can imagine, like this can get more elaborate, but this is kind of like the seeds of that. So this is basically like the function that updates your beliefs by like doing some math given by Bayes' rule, which is this. And it's just, you kind of just have to trust the math, which is what I'm not doing right now because this probably doesn't work. I think I probably did the math wrong is what I'm saying. But we'll find out. But yeah, so I kind of wanted to do this mostly to kind of give a sense. So my last thing I'm going to say, and I know like I'm over time by a lot, but so where does this leave us? So as I said, I was kind of trained in Bayesian modeling, where you're kind of thinking about uncertainty a lot. It's kind of like, I want to act under uncertainty. I want to make decisions under uncertainty. I may not know exactly what I'm looking at. I may not know exactly what I'm hearing. I'm in a noisy world. So Bayes is kind of like the language of how to deal with that. So that's kind of like the place you go in your toolbox when you're confronted with a problem where like uncertainty is like important. So this was like a little Bayesian model I did of convention formation. So basically like, you're trying to infer something that will hold across everybody from observing only a finite set of people. So that's like a generalization problem, and you can write it down in Bayes. But something that kind of blew my mind when I first came across it is that like, that's not the only way you can think about this. Actually, a totally equivalent way of writing this down is as a meta-learning problem in like deep learning. So you can think of all of those parameters that you were previously doing Bayesian inference to like learn as like points in a big space, and think of this more geometrically. So as you observe things, you can use the likelihood to take a gradient step in the direction that makes the data more likely, which is exactly what Bayes' rule is doing. So gradually you're kind of like getting closer and closer and closer to your partner's true beliefs, which you can kind of think of as like loosely like updating your belief distributions, assign higher and higher, probability to the like true ground truth thing of your partner. So that's kind of like this part of the model where you're like using the likelihoods. The like part that's like maintaining uncertainty turns out to be equivalent to a regularization term. So actually like the kind of classic way of regularizing neural nets came from like thinking about this equivalence. So when you do like L2 weight regularization, you're basically using a Gaussian prior, turns out mathematically. And then if you want to do meta learning, there's this kind of hot technique in kind of neural nets called model agnostic meta learning, which is basically doing a double gradient descent. So you're taking the gradient of these gradient steps and using that to update your initialization. So that's like something that was introduced in the last 10 years. And it turns out that this can be shown to be equivalent to a hierarchical Bayesian model. So that's kind of a nice result. And it kind of like, what I'm trying to argue is like having the flexibility of like going back and forth between these. There's some problems where like this is much more natural, especially if you're trying to like scale up to natural language and can like instead of using that little L function, you can use like a 9 billion parameter neural nets as your lexicon, right? And like this parameter in space is not just like a particular dictionary, but is like parameters of GPT-4, right? Of like something that's actually producing real natural language. And then the kind of last little link that I wanted to show here is that, and this is also a little bit of like a response maybe to Jonathan's talk, is that actually if I'd done animations, I would have hidden this, so ignore this side of the slide. So what you're doing in Bayes' rule is you have latents and you have a forward model that gives you observables. So this is like beliefs, desires in people's heads. This is things you can see, like their facial expressions. And the kind of like currency of Bayesian modeling is you have to write down what you think the connection between those is in that direction. And what Bayes does is it fills in the other arrow in a very kind of like costly way. But this idea of amortization, which is related to Stefan's point about dynamic programming and caching, that's like one kind of amortization. Another kind of amortization is to just train a neural net to go from observables to latents. So it's just another function. It's not driven by Bayes' rule at all. It's just like a big neural net that takes these in as input and tries to predict these as output. And you can like train it using a likelihood. And this is called a variational autoencoder. So this is actually like basically a way of like short circuiting Bayes, so that instead of having that like big posterior function that takes forever to compute, you just can run an observable through this model and just get output. Like it's just in a single pass. It's not like an algorithm at that point. So this is called like an amortized inference model. And there's a lot of theory about that, but it's basically like, I think one response to like, wait, how do we do theory of mind when like the world is so complicated? And I think that this is kind of increasingly, like you can actually show that if you train a model to do this, so you see observables like some state of the world, you run it through some gigantic neural net with a billion parameters, and you make predictions about what the agent is going to do next. It turns out that in tractable domains, this gives you Bayes' rule, which is kind of crazy. So like basically you like reverse engineered Bayes' rule by being like, Bayes' rule is the thing that allows you to make predictions given observables. So if you've trained that well enough, you've basically got like a working approximator that you can just run a single pass through really cheaply, make predictions. And I'm glossing over a bunch of details here, but I think I was mostly just trying to like intrigue you a little bit. But I think that the idea, if you want to think about kind of like computational models of cognition, is like if I had like a single tutorial piece of advice, is like, don't get hung up on kind of like camps of models, because like they're all interrelated and they each let you see the world in a unique way. So thanks. I know it went way over, sorry. I don't know what the next thing is.
Next one, the hackathon. So I guess questions for yeah, sure.
Sure. Yeah, I don't know if like that is, yeah.
This is sort of against what you just said, but did that last realization make you more Bayesian?
I think it made me feel like I could be Bayesian without, or like
Without fear.
without fear. No, I mean, I think that it kind of just like is satisfying that you can. So I think that this is the way that my advisor thought about it, is that like, you know about Mars levels, okay, MAR. So Bayesian models are usually presented at that highest level, a computational level, where they're not really intending to make claims about like what's going on inside here. They're just saying like, there's a normative thing, which is like, if you observe these things and you believe these things, this is what you should think afterward. right? It's just like a normative kind of model of that.
Not descriptive.
It's not descriptive. Yeah, it's just like, so it's kind of like a stick where there's kind of this idealization. And I think that that is like, has been enormously useful for getting traction on problems, especially in social cognition, where the kind of more detailed models are really weird, right? Where like you kind of need to gloss over the details because it's like you don't even have like a working characterization of a phenomenon. You don't even know kind of like what the latent variables that might be relevant are. So it kind of is useful for working at that level without needing to think about like, oh, what hyperparameters of my gradient descent algorithm should be and stuff. But I think that like, once you get into doing naturalistic stuff, and this is kind of like something maybe my like third year of grad school I got very concerned about, is like, I really want to be able to like do social cognition based on like the actual data a human in the world observes, which is like, I get all these pixels in my eyes, right? And like I hear these words and it's like very high dimensional, right? And like the classical stuff out of the Bayesian toolbox is just not tractable. And like that amortization stuff is kind of like the modern way of doing Bayes anyway. It's like variational inference is what it's called. And like no one really does the old things anymore because like they just don't work in high dimensional spaces. So we've kind of already left behind a lot of the like old ideas of like how to do inference because they just aren't tractable. So I think that like in all of that, by the way, variational inference is like a optimization, like a neural net based optimization method, basically. So like all Bayesians, including like, you know, people that are in statistics departments doing Bayesian statistics are basically like running neural nets to like fit their Bayesian models. So it's not really like either or. So I think that it's kind of like, and vice versa, like people in deep learning, there every year there's this like uncertainty in AI kind of conference and like Bayesian deep learning, because like there's a bunch of things that deep learning is bad at where it will like overfit. And it turns out that like porting in some of the ideas from like Bayesian world gives you like more robust like neural nets. So I think that this is kind of like boundary breaking has been like a productive thing. So that's the way it makes me feel, is kind of like I like what Jeremy was saying earlier about like, I just feel like I understand how this stuff works a little better than I did before by seeing the commonalities. But then I think that like from the view of a working scientist, it's like I often in the same project will like come up with a little Bayesian model that allows me to like think more clearly about the problem because it like writes it down in a very like concrete like way that I can kind of like see what the predictions would be. And then if I want to like do it on real facial expressions or something, then yeah, I'm going to need a neural net for that. Like I'm not going to try to write down like a little hand fryer over that. Like that's not, yeah. Yeah.
Especially in this whole.
Yeah.
On the other hand, I guess, you know, speaking to me personally, this means like I have to learn like two things.
Yeah.
The managing like blah 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 built like integrated. Get like you think that's going to be prohibitive, I guess, or is it going to narrow the scope of the people?
Yeah, that's a good question. I think that this is like, you know, as educators, things that are complicated get like simpler over time as people try to explain them better. So like, I do think that like, you don't need to know like all of Bayesian everything and all of like deep learning everything to like do this, right? It's like kind of in fact, like you can, in some ways, this is nice because like a bunch of the stuff that you usually have to learn in like a Bayesian statistics class isn't really relevant in these domains. So you can kind of just like throw out a big part of those textbooks. And then hopefully we can kind of like, so there are tools. So like there's these things called probabilistic programming languages. And this is why I was like being a little bit like self-deprecating about my ability to like write this in vanilla Python, because I've gotten very used to these like things that hide a lot of the complexity for you. So you basically just write down this part, which is just like given like a description of what I think the latents are and their probabilities. I just tell it like I expect the observables to be this, and then I just hit a button and it like gives me posteriors, right? So I don't have to like do any of the stuff on this side. And like those tools, I think they feel like coding in a normal programming language. So there's no math involved, which I think has helped a lot, where like, in fact, like you get so used to writing it as like a program that like when you sit down to write your paper and you're like, oh shoot, I have to put this in a PDF. Like I have to translate this back into math somehow. And that's why like in a lot of these papers, the math is like incomprehensible, because it was like actually not really meant to be math. It's like easier to think of it as like a for loop or something, right? It's just like, you can't, I don't know, at least like people are not used to putting that in like a scientific paper. So it's like, yeah. So
in other words, you're kind of saying, don't be scared of it.
Yeah, don't even think about the math. Honestly, it would be my advice. I think that like often it's easier to just look at the like code. And it's like, sorry, I love math, but like it you know, because it's fun. Like, and if it's fun for you, then you know, do it. But you know, I think that like they can be equivalent in the sense that they like express the same thing, just like in a different language. So like use the language that like makes sense to you.
Maybe on that happy note. So Robert, are you gonna stick around? Because I think people could continue talking if they want, or we can move on to projects. And so let's thank Robert for